Well, good afternoon. Welcome back, everyone. This afternoon we'll be focusing on the Constellation project with briefings from NASA. The committee has had the benefit of a number of briefings previously. Today will be, I believe, the final briefing, the formal briefing that we receive. We're indebted to the folks on the Constellation project for the support and effort they've given us. In fact, we're indebted to a lot of people at NASA and elsewhere, and it's dangerous to start naming names. So, but I do think there's one person that the committee here has to acknowledge, and that's Donna Cannell, who has kept this whole committee on time, well fed, if not well slept. The first speaker will be Jeff Hanley, whom I think everyone in this room knows, who we've had the privilege of speaking with at some length before. Jeff, thanks for joining us again. The floor is yours.
Okay, sir. Thank you very much, and thanks for having us this afternoon. We're going to talk primarily about ground operations as it pertains to all the activity we have going on here at the Kennedy Space Center this afternoon. Before I get into that, just a couple of offers to the committee. We resonated very much with Jeff's comments this morning on probabilistic risk assessment, and we offer more dialogue on that. I think we find ourselves in pretty well agreement on how the program is applying that, and we'd like to share that more of that with you. On the commercial engagement, it's we think important to point out that 80% of the Constellation budget goes to industry. We have competitively procured these contracts. The subcontractors, some of whom you've heard from yesterday during the public session, all are engaged and working toward the Constellation goals as we've laid them out. And then on internationals, we'd offer that also more dialogue on that, General Lyles, on what we've done in the Constellation program these last 3 years to get going with our international partners on the Constellation Lunar Surface Systems activity. This afternoon, as I said, our focus is ground operations. We have here at the Kennedy Space Center a great legacy from Apollo through the shuttle program to today. We have the shuttle team is processing our first test flight. It's the Space Shuttle USA workforce that is today stacking the Ares 1X rocket, and we're enjoying great progress there. Pepper Phillips is going to provide you an overview of what we've done here at the Kennedy Space Center on launch infrastructure. I would point out that there are other parts of what happens here at Kennedy that we unfortunately won't have time to touch on, that being the fact that the Orion factory is here on site in the ONC building, the building that used to be used to process the Apollo spacecraft. And then also manufacturing for elements of the first stage of the Ares 1 also occur here on the Kennedy Space Center premises. But today's focus is operations, and I'm going to hand it to Pepper.
Let's see. Thanks, Jeff. Good afternoon, Mr. Chairman, and good afternoon to the panel members. My name is Pepper Phillips. I manage the Ground Ops project at KSC. Like my colleagues, I recognize the importance of the work you guys are doing and the effort you've got in front of you. It's a difficult task. I hope not to add to that today. What I'd like to do, next chart, share with you some of the progress, and I do appreciate the opportunity to talk about the progress of the Ground Ops project. What you see on this first chart here is our exploration capabilities chart. Again, this is a chart that you guys have seen before. What I'll tell you is the Ground Ops project is the enabler for the broad capabilities that the Constellation program has. Next chart. What it lies here is the specific goals of the Ground Ops project. These flow down from the NGOs that you guys saw and referenced earlier, from ESMD through the Constellation program and down to us. These are specific for the Ground Ops project. What I intend to do today is talk you through those goals and what we're doing related to each and the progress associated with each. So next chart, I'll start you with goal one, that being develop the ground infrastructure, and we are to leverage existing shuttle and International Space Station assets to meet the Constellation mission. Next chart. So when we started down this venture approximately 4 years ago, the first daunting task was to make sure we had a launch complex baseline. And what we attempted to do was to step back and say, is the infrastructure that we have appropriate and appropriately sized for the architecture that we're planning on embarking on? We went and kind of looked at the trade space here on the East Coast and kind of looked at the Eastern Test Range. Came up with a number of options that outline what potential trade space we could go look at. Part of that was complex decisions for Ares 1 and then associated complex decisions for Ares 5. Ares 5, of course, as you know, ESAS was sized for the Launch Complex 39 infrastructure, and it is limited on what it can do because of its size. So we looked at Launch Complex 39 as outlined in ESAS. We also looked at a new launch complex for Ares 5. We had a little bit more flexibility on the Ares 1 side. We actually looked at an open complex, Launch Complex 40 at the time, that is now being utilized by SpaceX. But we went and looked at that infrastructure as well to say, is that an option for us, and does it provide any benefit to us in our emphasis on how we execute ground operations? Ultimately, we chose the Launch Complex 39 area and its assets mainly for a couple of reasons. Biggest being life cycle cost. As it played out, life cycle cost utilizing the assets that were available from shuttle turned out to be the by far standout life cycle cost profile. It did have cost benefits, but it had some other benefits as well. It kept the architecture in a common area. It capitalized on the knowledge base that exists within the executing operations team. So this was the first trade study that we went and executed, and from there we'll narrow that trade space. Next chart. These next couple of charts will kind of tell you what we looked at when we evaluated the complexes, specifically Launch Complex 39 and Launch Complex 40. The first chart here shows Complex 39, and what you'll see is there's a number of assets available at this pad that are coded in green, which means they're available and ready for use for the architecture for Ares 1. The yellow and red were areas that we either had to work or something that we couldn't use, but the condition of Complex 39 was very favorable for the Ares 1 vehicle. Next chart. Conversely, you look at Complex 40, and there were a number of systems that were either in the demolition state, had been removed, were not available for use, or didn't fit the needs of the Ares 1 vehicle. So we quickly dismissed Launch Complex 40 as an option. Next chart. This kind of outlines what I was telling you. There's a couple of areas we looked at, both development cost and life cycle cost. If you'll notice, the profile of the Complex 39 and Complex 40 shows that the Launch Complex 39 is significantly better in terms of development costs and life cycle costs. Next chart. Okay, the other areas we looked at was Launch Complex, and Launch Complex 39 was the VAB and crawlerway assets. One thing the shuttle program has done and done well is maintain the VAB as a facility system. We did capitalize on some of the hurricane funding several years back, and in fact have rehabilitated the VAB into a fairly good state. If you hadn't noticed from standing afar, it does have new siding on the side, so it looks real clean. It's got a new roof. VAB doors have been modified and improved, and it's got enhanced hurricane protection, all yielding lower O&M costs. We, in turn, will have to do a few specific things in order to execute this program. Notably on this page, we'll be installing cable raceways specific to this architecture, and that'll keep it clean from the existing architecture that's in the VAB. Other assets that we looked at was a crawlerway, and in fact the crawlerway system. Again, what we've done is done some studies of the crawlerway and its capacity It is in good shape. In fact, the Corps of Engineers did an outstanding job when they built that crawlerway back in the 60s. So that's another asset that's in really good shape that we're going to capitalize on. Next chart. So that was essentially an initial baseline that we went and looked at. The launch complex trade, the crawler and the crawler transporter trades. What we wanted to do was dive then down into a deeper level to look at potential options to get us an updated baseline, which is kind of what you see in that middle block. What I'll tell you from this page is from guidance that we received, certainly from our NGOs, the needs, goals, and objectives, and communication down from the program, operability is the driver for our operations concepts and has been driven from the start. And I'll talk about that some more as we go throughout the day. Next chart. Okay, one of the first things we did after establishing our initial baseline was we opened a broad area announcement, opened it to industry. We had 4 major contractors, aerospace contractors, that were awarded a 90-day contract. You see them listed there on the left side of the page. Our general guidance to them was the same that we took, which was your range of options are limited to the Eastern Test Range as a launch site, and from there it was up to them to determine what were the best options for us to go pursue. They in fact conducted their 90-day studies. They gave them back to the NASA team individually, and then once we had evaluated them individually, we then sat down with the group as a whole and debated the relative merits of each proposal. What you'll see there is they largely validated the concepts that the NASA team had come up with. Mainly, Launch Complex 39 was the best option. Several of the others you see listed there, I'm going to talk a little bit more in depth as I go through the trade space. But I'll note that we also found some bright ideas from the industry and the aerospace community that we adopted and further studied in our subsequent analysis. Next chart. Okay, so the first area we looked at was the launch pad. Our trade space was really centered around whether or not you affect every operation at the pad or you do things prior to getting to the pad. What we had was stack on pad and a service on pad option, a mobile launcher concept that also serviced on the pad, and a mobile launcher and a clean pad concept. The stack on pad option was really a non-starter in the limitations of the lifting requirement, in effect a bridge crane that's able to lift 175 tons worth of capability. That largely limited you, not to mention the exposure that you have while you're trying to do those hazardous lifting operations. So we kind of focused on the mobile launcher concept and the service on pad. Our studies indicated that if you kept the services off the pad, much like the Apollo community did, where you didn't have a fixed infrastructure, the pad that you had to maintain, there were significant O&M savings that could be realized by not having to build the infrastructure and maintain it at the pad. Also, we found that minimizing pad processing time helped with our critical path timelines and helped us with our launch availability, which were key attributes that we were looking for. So we settled on the mobile launch clean pad concept. Next chart. A couple other features that are on the pad I wanted to talk about. Obviously, Bob Cabana talked about the lightning protection system that we've put into effect out of the pad. It's a 3-tower, 600-foot tower Faraday cage protection system. We started out on a study, much like our ELV counterparts, with a 4-tower system. Our engineers did an evaluation and figured out the geometry of the Faraday cage and the catenary wire system such that a 3-tower system became a better option, and that helps in the certainly in the development cost and the O&M arena. So the lightning protection system is off and running. Also, the emergency egress system was another system that we evaluated. Right now, the shuttle uses a slide wire system. We, in fact, gathered key stakeholders, including the flight crew office, human factors personnel, the health and medical team, and did assessments on future and better potential emergency egress systems. They included things like the slide wire the shuttle system uses, a slide tube, elevators, a rail system, and escape chutes. After that study, the team came to the conclusion that the rail-based system was the best system, really in effect getting the crew away as rapidly as you can in a controlled environment. As of today, we're still using the bunker option that the shuttle pad uses, but it's a much safer system, much more reliable, robust system, so the team decided on that rail approach as the best option. Next chart. Okay, so from an accomplishment standpoint on the pad, the lightning protection system is obviously the horizon-changing event at the pad. It's something really notable. We're about 91% complete. Still need to install the catenary wire system in its entirety. We do have a portion of that system installed already, and it's planned to support Ares 1X for its mission. You see FSS and RSS demolition design, that's 100% complete. We're expecting to pick up with that demolition start March of 2010. The emergency egress system design is nearly complete, and we expect to have CDR for that system in October of this year. And we have completed pad PDR overall and expect to effect its CDR in October 2010. Next chart. A couple of accomplishments specific to Ares 1X. What we're doing with the Ares 1X system is unique. We're using the existing assets and infrastructure of the shuttle in order to be able to launch Ares 1X. You'll see on this page at the top really things that we had to remove in order to prepare the pad for Ares 1X. The lightning mast on the left, GOX vent arm in the middle, and then the removal of the orbiter access arm. All of those are complete. Then at the bottom of the page, you'll see where we needed to install assets to gain access to the Ares 1X vehicle and its unique configuration. So you'll see we installed upper stage system access and also the FSAM access, both left and in the middle. Vertical vehicle stabilization system is being installed, so it's the ports you see there is being assembled on the pad surface. Next chart. Okay, moving on to the VAB, I thought I'd walk you through some of the trade space that existed there. Really the big driver for us was whether or not we use the existing platform system in the VAB or go to a new VAB platform system. Again, the biggest driver here for us is cost. So we looked at the relative cost options and the access requirements that we had. One thing we found, and by the way, from a historical standpoint, when Apollo converted to shuttle, they used the existing Apollo platforms and modified them to fit the shuttle configuration. Once we got in and looking at the requirements, we found that there was a load margin issue on the VAB if in fact we had to modify the existing platforms. So it was prudent for us to go ahead and install new platforms that lessen that risk of maximizing those loads. So that's one of the things we did. The other thing this new design does for us is allow individual platform and individual platform access to the areas that you need. If you'll notice on the top drawing, they're kind of ganged platforms where when you slide one of the existing platforms against the vehicle, you're essentially drawing 3 or 4 different levels of access up against the vehicle. That, from an operations standpoint, is a little bit cumbersome because all operations need to be complete or at least in a secure state before you exercise those platforms. And this individual state that, and then the new version, it is much more clean and it's better for the operations teams as they execute their tasks. Next chart. So for accomplishments on the VAB, you'll see that we have completed 100% design for the platforms, and we've in fact released a RFP to industry for construction of those platforms. VAB PDR is completed, and we're looking for CDR in October of 2010. I'll point your attention to a couple of the pictures there. You'll see on the left side of the page, removing a C North platform, which was an interference platform for Ares 1X configuration specifically. That has been removed. In the middle of the page, you'll see a separate upper stage platform that has since been installed in the same high bay. Next chart. Okay, I'm going to skip the next two if I could. These are both operations progress for Ares 1X, and Bob S. is going to speak to those. So page 20, if I could. Okay. Okay, I'll move you to the mobile launcher trade space. When we did some evaluations on what our options were for mobile launcher, we really looked at being able to use the existing shuttle assets versus a new mobile launcher. And again, this is for Ares 1. The biggest driver here was availability of the mobile launcher assets. Shuttle community is using 3 mobile launchers and continues to use 3 mobile launchers. They have made available the 1 mobile launcher for Ares 1X. Being able to execute that mission and, in effect, build a new design with a launch tower on it was not feasible. So that drove us specifically for Ares 1 to a new mobile launcher. That did a couple of things for us. It reduced the weight. Since we are, in fact, going back to the Apollo configuration with the launch tower on it, now you've got this rocket with its solid motors. You've got a big tower planted on top. So we have to watch the load margins on the crawler transporter. This does reduce that weight, the specific design does. And it does provide flexibility in retrofitting and reduced O&M cost. Next chart. Some further trade space we went off and looked at while we were looking at the mobile launcher concepts and, in fact, operations in the VAB. Our team came up with a concept of offline stacking, and this is really a critical path time driver where we could, in effect, stack the first stage offline and keeping it off the critical path while we could do other operations. We looked at a separate offline stacking facility. Again, cost prohibitive. It would be in the realm of about $500 million to build a new facility. But the team pressed further and looked at options that said, hey, I could potentially build that offline stacking capability right there in the adjacent to the integration cell in the VAB. It was a very innovative concept, and one, in fact, that the Constellation program really liked. The problem was the requirement for development costs and construction costs were in a very bad time period for the program. So it was determined to be cost prohibitive for the immediate implementation of that option. One of the things we found when we were looking at that option was you required a launch mount, which is the lower right-hand picture, in order to be able to affect that option. We did look at the launch mount independently while we were doing this study and said, even if we cannot put into effect this offline stacking, this launch mount concept does allow for a better turnaround because you can work the turnaround of the launch mount offline. And in fact, when you have 2 launch mounts, you can have one that's refurbished and ready to go and take the other offline so it's out of the critical path. So again, from a time savings, the launch mount was very valuable. The other thing we liked about the launch mount it allows you to make changes to the vehicle, minor changes to the vehicle, either in height or specific requirements that exist in the hold down mechanisms in the launch mount. We were able to effect those changes in a singular unit where you don't have to take the entire mobile launcher offline in order to effect the changes. So a lot of flexibility provided by the option, and this is one that the Constellation program asked us to pursue. Next chart. Okay, a little further in the trade space, we looked at several options on T0s. Again, we have a lot of history here, have the benefit of the many of the programs that we looked at. We also have done a lot of benchmarking of other programs, including the ESA community and the Russian teams. Concepts. What they came out with was a tilt-up umbilical arm, and it was really selected for its operability benefits, namely that it's a simple mechanical counterweight design, and it's highly reliable. It doesn't use any hydraulics or pyrotechnics in its operation. So in fact, we have pursued that design. It is a common architecture that we can use across multiple T0 locations, and in fact, we've got prototype testing underway. Next chart. So this is what we ended up with as far as a mobile launcher for a final concept. Again, the the new mobile launcher you see on the left, with the launch mount, bottom right, and then the TUA concept, tilt-up umbilical arm, at the top of the page. Next chart. Okay, from an accomplishment standpoint for the mobile launcher, you'll see here we're about 51% complete. That's on the structure itself. We still have a ways to go on outfitting, but what you see in red here is that structural completion pieces. The red on the square on the left there is the mobile launcher base, and again, it's standing offline. Bob showed a picture of that, and I'll show a couple subsequent pictures. It looks fairly complete, and I hope you get a chance to go see it while you're here. The tower itself is being constructed in tiers or pieces. What you'll see when you go visit that mobile launcher is you'll see a lot of these tiers constructed already to the side, so you can see predominantly nearly all of that structure is in its individual tiers completed. Next chart. Okay, so these are the pictures I promised about the mobile launcher. You see the base there and at the mobile launcher refurb site that's being constructed. On the right side, you see a flooring of that base, so you see it's getting enclosed pretty well. At the bottom of the page and on the next page, you're going to see several pieces of those tiers that I talked about. Again, those are to be assembled separately on the side, and then we're going to stack those tiers on as we get ready to do that to construct the tower. Next chart. Again, a couple of more pictures of those tiers as examples. Okay, moving into other areas that we're developing. Launch equipment test facility. Again, this is a Apollo era test facility that we've used for the Apollo program, subsequently for the shuttle program, and now we're using for Constellation. It is really our test and verification area. We've made quite a substantial progress on this. I told you about the tilt-up umbilical assembly. You see that in the middle of the page. That's where we're doing our prototype testing. We also have several other areas that we're in fact developing and will be using for that verification testing. Things like the vehicle motion simulator, cryogenic systems, hazardous gas detection systems, etc. So we've got a lot of development underway and making good progress there. Next chart. Okay, we talked a little bit about the pad option and offline servicing. Original concept we had at the pad was that we were going to do all the servicing on site. As we conducted the trade space, there were a lot of advantages to taking that critical path work and taking it offline and bringing it out of the critical path. There was also the advantage of doing some of this hazardous work in a controlled environment and not at height as you would have to at the pad. So we studied options about how we could do that, and trade space was doing hazardous processing servicing on the pad or doing it offline. We looked at some facilities that existed across Kennedy Space Center, one of them being a fairly new and little used facility called the Multi-Payload Processing Facility. It was built by the station program, I think to do some propulsion work that it never eventually came to the center. So we had a real opportunity to use a facility that was in good standing and good shape to do our offline servicing. So in fact, we effected that change, and our new baseline became doing hazardous processing servicing offline. Next chart. As far as accomplishments in that area, we're really in the design phase. This one, the modifications of the facility, since it's in such good condition, requirements are very few. We're still working with the Orion project to understand what exact requirements we have. So we're right now under the facility modification and design review state. We're at the 30% there. Similar with the GSE that goes associated with that facility, and we have completed a PDR for that particular development. Next chart. Okay, a different system, command, control, and communication. Again, our team did a lot of benchmarking of other systems to look at the command, control, and communications capabilities that these systems brought to the table. We also have a rich heritage with the knowledge base that we've gained on the different programs that we've flown. So we narrowed down our trade space after looking at all those options to some of the existing systems that we have, namely the LPS system that the shuttle community uses, TCMS, which is what the space station community uses. Atlas V derived architecture, because we had a lot of experience from our friends across the river. And then we looked at standards-based architecture, which is really a open platform that uses COTS hardware. This one seemed to be a fairly simple answer, and it was. Once we got into the trade space, it was readily apparent to us that from a cost standpoint, open architecture that highly leverages COTS was the answer. The supply chain, the ability to service the equipment, the ability to change, and not keeping things unique for Constellation all seemed to pay off in the overall life cycle cost of the CCC system. So in fact, the standards-based architecture is what we chose. Next chart. Okay, thought I'd walk you through some of the accomplishments associated with command and control. We have, in fact, modified our firing room 1, which is a young Crippen firing room. You'll see at the top right of the chart a couple of graphs that show that same firing room in use both for Apollo and Shuttle. At the bottom left of this page, you'll see where we started to do our modifications to that facility, and in fact have completed the facility modifications, and it's ready to go for Ares 1X. That middle chart, or the middle picture you see on the right-hand side, is the configuration we'll be using for Ares 1X. And in fact, we held our first launch sim on the 22nd of that facility, so it's up and supporting. The bottom right picture is the final configuration, which is will incorporate the entire vehicle, and that's how we plan to be able to exercise the room, as you see there. Next chart. Okay, so after all of that trade space, that got us to a baseline of what you see here. What we essentially have is a single string capability for Ares 1 and a single string planned capabilities for Ares 5. Namely, we have one VAB integration cell for Ares 1, one mobile transporter available for that mobile launcher, and then a pad LC39B specifically for Ares 1. We use a similar set of assets for Ares 5, and you'll see those listed. Next chart. Okay, and from a facility standpoint at Kennedy Space Center, these are a list of the facilities that we intend to use. The majority of them are heritage shuttle assets, a couple of those being ISS assets, specifically the MPPF and the SSPF. Next chart. So what we've got with this architecture and its single string is really a pretty grand flexibility, extensibility, favorable architecture. We're pretty proud of the fact that we have, with this clean pad mobile architecture, we are able to scale as we require the asset. So what we've done with this single string asset is determine our own flight rate. And with the assets we have, we're able to meet the near-term flight rate of the Constellation program. If the program decides that they need to operate at a higher flight rate than we can provide, we're able to buy additional assets that will enable us to go do that, namely things like an additional mobile launcher, and we've got other high bay assets in the VAB. You can also affect even higher flight rates for things like I described earlier, the offline stacking capability, which we have not precluded, and an integration facility out towards the pad, separate from the VAB, we were calling a vertical integration facility. We could also affect those changes. The other thing this architecture, ground architecture, does for us is enable us to fly vehicles of different configuration but like size. As you're well aware, the flame trench size for Ares 5 was compatible and enabled the design of the Ares 5. It is the size Saturn V class flame trench. So we can operate systems in that same class from this infrastructure. Same thing with the clean pad concept. Really, the mobile launcher serves as an adapter between the vehicle and a generic launch pad. We have our VAB integration cells that are available and can be configured for different configurations. And in fact, if you actually wanted to pursue a vehicle of a different height than is limited by the VAB itself, you could build a integration facility that's taller than the VAB if so chosen. Of course, you can only get so tall, and we have built the lightning tower protection out at the pad to be appropriately sized for what comes out of the VAB, but you do have some flexibility in the size or the height requirement. Next chart. Okay, progress-wise for our schedule, you'll see that we have completed our ground ops SRR and SDR, and we're proceeding towards PDR. Expect to accomplish PDR in the fall time frame, in the spring of next year. One thing you'll also notice on this page is the major development operations for Ares 1 are well underway. You'll see that the PDRs are well behind us, as I've mentioned, and we're approaching CDR. Next chart. Apologize for the kind of busy chart here. My intent is not to drive you towards a specific detail on the chart, but I wanted to point out that we do have a lot of procurements and procurement efforts underway. So there's really two messages here. One is we're well underway with procurements and contract efforts for this project. The other message here is that the NASA team is the lead of this. We don't have a prime. We are, in fact, managing these contracts ourselves and doing the integration effort ourselves. Next chart, and the next, please. Okay, so from there I'll move you into goal 2, which is ensuring ground operations are considered in flight hardware designs and manufacturing. Next chart. Early in this program, one of the leading themes was we're going to drive this to be a highly operable system. Some of the criticisms in programs past, and our friend Bo has been very aggressive in making sure we met these challenges, was a lot of times they felt like the development efforts didn't consider ground operations and the cost that it drove to not have it considered. So we were asked early to make sure that we drove from our knothole with expertise that we've gained in the ops world, drove it back into the flight vehicle design. So early what we did was establish teams of these highly skilled expert operations folks to go live with the design teams for the flight vehicles. We have in fact done that, and we've had great success in affecting their designs. It was a little bit interesting because we thought when we first started we would be, the design teams are so focused on meeting the technical objectives that they would push back on the operability inputs. What we quickly found once people got accustomed to the idea of operability being a focus was they couldn't get enough of the operational expertise that existed at KSC. So we quickly started making gains and driving operability successes into their designs. The 2 pages you see here, both on Orion and Ares, do that. And no, I'm not going to go into the specifics of those unless you'd like me to, but they more or less capture things that are important to the operations community to drive costs, drive capabilities, drive number of people that have to execute the operations. It's really the assembly, service, test, and monitoring capability that we're worried about, and the flight design teams have responded very favorably to the suggestions that we've had. Next chart. And again, we've done that with both flight systems, the Orion and Ares 1. Next chart. Okay, I'll move you into the last goal, which is really develop ground operations methodologies and implementation strategies, including cost and schedule for pre-launch, launch, and recovery of program elements. Next chart. Okay, this is the nighttime job of the daytime job that we have, but this is the operations planning and analysis piece of the responsibility that we have. So we're really building the plan for how we're going to execute operations at this center. So we've needed a couple of tools and to drive out exactly what it is how we're going to operate this vehicle. When we started early, we had initial concepts. We planned those concepts. We built budgets against those concepts. As we've matured in the design, we've gotten to a point where we need to develop lower level detail. The first bullet you see there, the ground operations planning database, is that lower level detail. We have volumes of work requirements that we built into this database. It looks at specific tasks as they're executed, at things like whether or not things can be executed in parallel. in some instances with some operation or serial critical path work. We've also started on the contingency requirements. We largely focus on nominal operations, but we're now delving into contingencies and how those will be handled. We also developed an integrated timeline that's really a tool for program at level 2. This is really to support vehicle change impact assessments. We report routinely to Jeff at his level 2 board about our progress on these timelines. And as vehicle changes are put into effect, they're measured against the timelines and determine whether or not we're improving on our timelines or we've, in fact, caused a problem in how we're able to operate here at KSC. We have several requirements that we're expected to meet at the program level. These are how we measure how we're performing against those requirements. We have discrete event simulation tools where we're able to look at trade studies and identify potential areas of cost savings. Similarly, launch availability and reliability analysis is conducted at the ground system subsystem level. We have design visualization techniques that really help us with operational impacts. And we are doing contingency risk assessment, prioritization, and analyses. These all look at high potential risk and how we can solve them. Next chart. And so we've spent a lot of time and focused a lot on Ares 1, but we have not taken our eye off the lunar planning efforts, and in fact have worked closely with the program to look at options and potential designs for the same infrastructure on the ground and how we can utilize the existing assets we have. So we have looked at several Ares 5 configurations and how that affects the ground systems. We've looked at facility concepts and transportation approaches and really how they affect processing timelines. Next chart. What you also see here is a number of trades that are in effect. Again, they're similar to the trades that we conducted on Ares 1, but again, we're going through the same process and hoping to develop the same level of maturity in the concepts and concept trades that ultimately yield the greatest bang for the buck. Next chart. So I'd like to summarize, essentially for this ground ops team, we've developed a very dedicated team of experts. We've tapped into a lot of expertise, not just shuttle, not just station. We have Apollo era expertise. We also have launch vehicle expertise from the expendable program that we've infused into this, hoping to embody the best of all of the operations experiences out there. We have contemplated how best to use heritage infrastructure and balance that with new infrastructure, and I think we've achieved that. I think it's a pretty good architecture that we formed. We partnered with industry. BAAs was an outstanding experience for us, and we've affected that since in the program. We partnered with the state of Florida for potential solutions and solution sets that can benefit both the state of Florida and the program. We have operability considerations that have been overtly driven into the vehicle and ground systems designs, and we've had many, many successes as a result. I'll tell you, the team has met all its milestones. SRs behind us, SDRs behind us, and the ground systems element PDRs, as you've seen, are all behind us, so we've made great progress and on schedule. And finally, I'd tell you that we're well underway on construction and operations planning, and we're on track for the 2015 IOC commitment. And that's it for me. I'll, Mr. Chairman, if it's okay with you, I think our plan is to complete the Constellation program briefings and then offer you opportunities for questions. So I'll introduce the mission manager for Ares 1X, Bob S.
Yeah. I should stop now, right? All right, good afternoon. Thank you very much for your time today to give me a chance to talk about Ares 1X. Pepper said, my name is Bob S. I'm the manager of the Ares 1X test flight. You can see on this first chart, 1X is what we call a developmental test flight. It's the first one for Constellation in the Ares Orion configuration. And a developmental test flight is a flight you do early enough that you can use the data to improve your design from both the engineering side and from the managerial side, so we understand we're on the right track. A big picture overview of our vehicle, and I know yesterday in Huntsville, Steve Davis, one of my deputies, went through this a little bit for you. A couple of things I wanted to point out. Just a reminder, this is a 327-foot long vehicle. It's 1.8 million pounds. It's being assembled as we speak over in the VAB, and I'll show you some photographs in a second. We broke this down into 5 major primary objectives, and then as a key secondary objective. First and foremost, in the lower left, is demonstrate controllability of an Ares Orion configuration and in a relevant environment. And what we wanted to do was take the Ares flight control algorithms, put them into a test vehicle. So we purposely built this test vehicle to be what we call dynamically similar. The flight control system doesn't know it's flying an Ares 1X versus an Ares 1. The bending modes and stiffness are similar enough to Ares 1 that the flight control should behave the same way. In addition, we designed the trajectory to fly the same dynamic pressure profile that Ares 1 does from tower clear up to about Mach 4. That's the critical phase of flight for Ares 1, so we get a very good test of how the flight control will work with a long, slender vehicle. Once we do that, we go up to the separation area. We separate about 130,000 feet, and we're using the shuttle 4-segment booster that we had. We don't get quite as high as Ares 1 using a 5-segment, but the 4-segment gives us what we need to do the ascent through the maximum dynamic pressure range up to the separation point. So our secondary objective is to perform that separation. Just like Ares, we have booster tumble motors, booster separation motors, and check out the operation and performance of those. And we get into an actual separation event. Now the good thing about our vehicle, we have a simulator, a spacer, to give it the same length as if we had a 5-segment simulator. So going uphill, we only have 4 segments of propulsion. Once we burn out, it's about 122 seconds, just like a shuttle. It's about 130,000 feet. We do the separation sequence. This is exactly like Ares 1. Ares 1, when it expands a 5-segment, will have what we have as far as our expended 4-segment plus a spacer. So we're using the prototype Ares 1 parachutes, 150 foot in diameter, cluster of 3. It is a key test for Ares for us to use these in this test with the same mass properties, the same staging and sequencing approach. So we expect to get superb data for Ares project for the separation. Of course, the booster will be recovered by the SRB recovery ships. And the upper stage part of it, you can see from the graphic, keeps going on a ballistic trajectory, and it will be end up in the water, and that part will not be recovered. So we have those key objectives: controllability, doing the separation, the booster separation sequencing. We're also teaching ourselves again how to put together a new vehicle. So the objective down on the bottom, number 3, talks about the assembly and recovery of such a vehicle. That in itself has been and continues to be a learning experience for the agency to understand how different this vehicle is from shuttle, teach us now on Ares 1X what things need to be changed, what things work, what things don't work, and we've already captured lots of lessons learned for us to use in Ares 1 so we can be smarter quicker after this test flight. Next page, please. Now the good part about 1X is that there's no more view graphs, it's all photographs. Everything we've designed is built is here in Florida. It's all being put together, and I'll just show you photographs of where we are. So the Orion Crew Module Launch Abort Simulator, this was designed and built by Langley Research Center up in Virginia. This is the top of the rocket, of course, and you see it complete here during its testing, and you'll see more of that when we talk about our Stack 1. So next page. Upper stage simulator, designed, manufactured by Glenn Research Center up in Ohio. Comprised of 11 segments that were shipped separately, put together into logical groupings, tested, retrofitted with instrumentation. Next page. Now the roll control system is a very interesting story. It's mostly decommissioned Peacekeeper 4th stage hardware. The Air Force gave us the hardware basically for the price of transportation. They had to decommission it for treaty reasons. And Marshall Space Flight Center, Teledyne Brown, took the tankage, the thrusters themselves, associated valves and regulators, repackaged it into 2 modules. We have 2 modules opposed at 180 degrees. Each was 2 thrusters to give us this roll control system in a very clever way. Next page. Now first stage, I mentioned the first stage is a shuttle booster. It's the same aft skirt, same thrust vector control, same 4 segments. It's identical to what we use for shuttle. We did not make any changes from that. What you can see in this photo, you'll see subsequent, is we also had the first stage guys through ATK build new hardware. They built that 5-segment spacer that I mentioned. Also built what we call the forward skirt extension. That's where the parachutes themselves and the sequencing hardware is all housed. Then the big frustum in the middle, which ties the two pieces of the rocket together, goes from the 12-foot diameter booster up to the 18-foot diameter upper stage. Next page, please. Avionics is another thing, and I should have mentioned up front that 1X really is an opportunity to take as much heritage hardware that we had available and put it together in a way that reduced our cost and our time frame from project initiation to actual flight. I mentioned the Peacekeeper hardware. I mentioned the shuttle assets. Now Avionics, through Lockheed Martin, brought the Atlas V avionics. So the primary avionics for 1X comes from the Atlas V rocket. So it's proven, there's a lot of history, it has a lot of technical support for it. It's all over the vehicle, top to bottom, as well as over 700 different measurements, which is our key secondary objective, to collect as much sensor data as we can. So we have 700 measurements to help us correlate our models for the engineers, so we're a little smarter after this flight. Next page, please. Bird's eye view in the vehicle assembly building, kind of a slant view. You can see basically a lot of our pieces there getting ready for final stacking. And this is all done in High Bay 4 in the vehicle assembly building. Once they're ready to be put together, the photo I showed you of the MLP and the booster is in High Bay 3, and it's all happening today. So next page. Real quick, from a confidence of the flight, this is a long, slender vehicle. We're using a flight control system that's new. It's primarily driven by how we set up that flight control and the bending characteristics of the vehicle. We wanted to make sure that our predictions were as we expected, so we have 3 modal tests on our books. We've completed 2 of them. Most recently, this one over here, this is what we call Stack 1, which includes a critical piece of the interstage, the roll control system, the frustum, and the 5/7 simulator. That's the part of the vehicle most susceptible to bending. We completed that. We matched our predictions. We completed a previous one for the top of the rocket and matched our predictions. And then in a couple of weeks, when we have the whole vehicle put together, we'll do one again on the full-scale vehicle and making sure that we match our predictions. Next page. All right, I'm going to go through. You'll see the hardware again. This way, it's through stacking order. So we have, quote, 6 stacks. One is called Stack 0, only because this is a current shuttle stack, no different than we do for a typical shuttle mission. This is the MLP and the VAB High Bay 3 with the aft skirt and with the 4 segments. That's been complete for a couple weeks. Next page. This shows you where we are today. On the right is a cartoon showing what part of the vehicle is Stack 1. Stack 1, as we were talking here today, was brought up and over, is on top of the shuttle booster. So right now, from the top of that purple line, top of the frustum area down, is stacked in the VAB, ready to go in its flight configuration. Next page. Stack 2 is a separate ballast segment and a venting segment you can see there. That is scheduled to go on Monday, this coming Monday. We'll take that stack and bring it up and over. Next page. Stack 3 has 4 segments put together. Inside it is platforms and ladders for access and a lot of sensors up and down the vehicle. I mentioned there's over 700 sensors on this vehicle for us to collect data. Next page. We get into another ballast segments, and the ballast segments correspond to the liquid oxygen tank in the previous Stack 2, which is why it's down low, and then Stack 4, which simulates where the liquid hydrogen tank would be for the Ares configuration. About 130,000 or so pounds of ballast in our vehicle. Next page. All right, the top of the wedding cake here, Stack 5. This will be about a week and a half or so. We get this one up and over. And again, you see a lot of protuberances on there, and that one is ready to go. Next page. All right, full-scale integrated vehicle. This is what it'll look like with the cartoon as it rolls out. It rolls out directly attached to the MLP. There's no stabilization system or hold down. It's the 4 hold down posts that will have the vehicle out until it goes to the pad. Pepper did a good job of showing you some photographs of the modifications that we made at the pad in a VAB to enable all this, so I won't repeat those. But we're quickly getting to this scenario right here. Our launch date is October 31st, and it's coming quickly, and we're going to be ready. Next page. That's all I had for 1X. I know you saw some yesterday. And then after me, Ed Mango will talk to you about the Constellation Planning Office, or whatever you call it. Space Transportation Planning Office, sorry.
Good afternoon. My name is Ed Mango, and good afternoon, Mr. Chairman and members. Let's see, I wanted to talk to you about a portion of the Constellation architecture and the Constellation program that deals with what happens when we get ready to go operate this system. And so what we've done is the Constellation program and NASA has put together a charter for how to go do that development, and that's what I'm going to talk about. So next page. And this is just our quick agenda we'll go through in the next page. Last fall, SOMD and ESMD, the operations portion of NASA and the development portion of NASA, got together and they said, let's go create this planning office with the scope of the planning office to figure out the methodology and our processes that we're going to go use, our corporate processes, to operate a human system as well as develop the continuation of future human systems. And the idea here is you're doing those in combination with each other. Once the Space Transportation Planning Office, which I represent, will turn into a program over the next couple of years, it will then, once the system is fully developed and certified, it will take that Ares 1 system and Orion and manufacture it, produce it, process it, launch it, fly it to ISS, and recover that system. And again, that will happen after the certification process is completed by Jeff Hanley and his program. Next chart is we're starting out slow, and I'll talk a little bit in a couple charts about why I start out now, but the idea here is to get started to understand what our processes are going to be and to build the corporate capability to go do this. It's going to take us a couple years to get there, and the reason for that is we want to be able to marry as much as we can into what Jeff Hanley is doing so that the operations program folds right into what the development program has given them. This is a model that is followed in many other areas of government, especially in the DoD realm, where they have a developing system or developing program, and the sustaining program comes online and participates with that development program to make sure that it can truly be operated. Next chart. This is not something that just started last December. NASA has been thinking about this for the last number of years, about 2.5 years, in which a number of studies were put together, because in the human spaceflight systems for NASA, we've not done this before, in which we had a developing program and an ops program that's going to take that developing capability and move it forward. So back in 2007, this was started by a couple review teams, and it was established, like I said, at the end of last year, and will continue for the next couple years in the planning state before it's ready to become a program. The idea it will become a program at the time we get through CDR, and then it'll be in combination, and I'll show you a chart here in a second, in combination with the development program. Next chart. Let's see, the next chart talks about our establishment of a partnership between ESMD and SOMD. I work under the SOMD side of the house, so the operations side, and of course we're very much tied into what Jeff Hanley and his program is doing. In fact, we want to be connected very closely. Once the first system, Ares 1 and Orion, are set to go to ISS, and that has been certified, then this Constellation Transportation program will go ahead and take care of the budget, schedule, and technical content of that system from that point on. This will enable basically Jeff and his team to go continue on development of the next series of development tasks and the development of those systems. And it frees them up from having to operate the system that we will have to go to ISS during that phase. It also allows the operating program, that's the program that I'm helping set up, to be able to get back to those folks that did the actual design work and worked the number crunching back during this period of time, and be able to use that skill when we need to, especially if we're bouncing against certification type issues. Next chart. So what is the timing for this? Well, we are really dependent, of course, on the development of the DDT&E effort by the Constellation program. Under the current schedule, it basically says that as Orion and Ares get to their test flights in 14 and 15, they will begin to back away after certification is completed, and we will then take the control of that particular system at that point. You notice that, that really there's a handover that's overlapping by at least a couple years, and that's on purpose, so that we know that after the first flight or two, the system is not operational, but we are doing operations with the system to get the ISS. So you have to have that overlap between the two programs, very important. At the same time, it doesn't mean we need to use 100% of the DDT&E effort in order to go do the operation. So it frees them up to go do the next series of developments in order to continue on with the exploration initiatives. Next chart. So why start in 2009 and progress for the next couple of years? I'm hoping this chart will kind of show what we're trying to do there. What we're trying to show is that we have to embed ourselves at the number of different levels. First, in the engineering level, we're going to have our future sustaining engineers now become part of the design teams. Pepper talked about how he's influencing the operability after the hardware is here at Kennedy and after we're assembling the hardware. In addition, we need to have flight sustaining engineers that are going to be looking at the hardware from beginning to end on the design and its manufacturing capabilities as well as its operating capabilities both during ground and also during flight. So today we have a limited number of those engineers, and each year we'll be increasing those numbers as we come up to full speed by around 2013 or 2014. At the next level, at the project level, we also want to be highly engaged with the individual projects, that is Constellation and Ares, to make sure we fully understand what the cost drivers are to their implementation of their design and their manufacturing capabilities. The idea here is we need to get to a point where we understand the sustaining production, we can make that as efficient as possible, and we can help influence the life cycle cost not only during the PDR to CDR timeframe, but also as we go through systems certification and qualification. And last is at the program level, that is between myself and Jeff. Basically, Jeff is going to use our organization as the ops and sustaining arm of his program as his program matures and wants to focus more on that ops and sustaining role as a day-to-day activity. And so it's that partnership that will allow this entire growth to happen over the next 2 to 3 years. The other reason to do this now is we have learned from our past that the time to learn about flight hardware and know how it's going to operate once you get on orbit is during the time you're going from PDR to CDR and during the time you're going through qualification and certification testing. Even today on the shuttle environment, when we find problems during a mission, there's many questions that we ask about what was the basis of the certification, what did we learn from that certification, and what were the limits from that certification. By enabling the operations program to get started now and get embedded into the development program, we will have that capability in order to have the answers to those questions when we're actually flying the systems in 2016 and beyond. The next chart is just a summary. Basically, it says it's good to start early at this particular point in order to get subsystem experience under our belt in order to follow the flight hardware evolution. We're doing that at all the critical phases, both at the subsystem level, at the SE&I level, at the program level, and also in the mission operations and MOD levels. We as NASA now recognize that in order to implement the full capability of doing an exploration architecture, we got to be able to operate a system while other folks within NASA are continuing to develop the next system. And we believe that this architecture that we've set up is going to go ahead and do that. And we're in full concert with what Jeff and his team are doing and getting closer to them every day. So that's all I had to present, and I'll turn it back over to Jeff.
Okay, I just have some closing remarks, I think, to kind of sum up what you've seen these past 3 days, these past several weeks of presentation material and response to questions and queries and so forth. First, on behalf of the 10,000 civil servants and industry partners, contractors around the nation that have worked on and worked to create the Constellation program, I want to thank the Commission for the opportunity over these last 3 days to highlight the 4 years of progress to grow from concept to real designs and hardware. In these closing remarks, I would like to take us back to 50,000 feet, if you would, and to revisit the decision space that underpins NASA's present constellation architecture, depicted here. We visited this chart many times over the past couple months. Through the last 4 years, NASA was given explicit guidance to define a program to meet 3 essential goals, those being significantly reduce the net cost of low Earth orbit access, and achieve unprecedented levels of crew safety, and extend the sphere of human operations beyond low Earth orbit, that is, from 250 miles to greater than 250,000 nautical miles. To achieve any one of these would have been a significant accomplishment. To contrive an architecture that does all 3 would be truly historic. As a nation, we are now confronted with some crucial and perhaps course-altering decisions in human spaceflight. Now we must ask, do we press forward or retreat to reformulate our strategy? How important is crew safety? Do we really need or can we really afford heavy lift? Why can't all this be done commercially? And maybe we shouldn't even consider exploration beyond low Earth orbit in the first place. For me, the crux of these challenges centers around the axis of risk and about what NASA's core purpose is. To me, it's pretty clear. NASA's value to our nation stems in part from trailblazing, from the government taking the risks that no one else can afford to take. In a word, risk is our business. Not because it is easy, but because it is hard, is the quote that Ed pointed out this morning, the wonderful and poignant quote from JFK in the 60s. Commerce is a consequence of exploration. The physical trails we blaze pull on technology, which pulls our economy, which pulls our way of life. The evidence of the collateral benefits echoes across NASA's 50-year history. Governments blaze trails, commerce exploits them, and economies grow. This is what the history of exploration and indeed of human behavior tells us. The Silk Roads, the mastery of the seas, the manifest destiny of our nation, all were driven by government-funded trailblazing. Government literally laid the track across America, and transcontinental commerce and immigration consequently flourished. How fitting that the Golden Spike sits just a few miles from where we will soon test the Ares 1 first stage rocket in August. In the human exploration of space, it is on the frontier we should be taking our risks. I believe most would agree today that the frontier in space is beyond low Earth orbit. But in order to cross the ocean, we need to have mastered crossing the harbor first. Thus, creating the safest Earth-to-orbit launch capability in history is teaching us the hard technical lessons that remain. What does it mean to human rate a launch system? How does one provide a high probability of crew survival if something goes wrong? The commercial sector will need these tough questions answered for truly commercial crew access to space to flourish. Until the risk is sufficiently low to bet on a return on investment in the cargo, be it crew or hardware. As you know, we are using Ares 1, derived from the investment we are making in heavy lift, to address these remaining barriers to human rating a launch system and achieve higher levels of safety for the first 100 miles of every exploration journey, so that as we push out into the frontier, the acceptance of higher risk to mission success or crew safety is toward the objective. Heavy lift addresses risk in another fashion. It stems from the unfortunate, inconvenient truths of physics. That being, God has made it a real chore to climb out of Earth's gravity well. The propulsive technologies of our time are nearly at the limit of what chemical systems can do. In our judgment, when the performance and cost are fully accounted for, to explore beyond Earth's gravitational influence within the next decade or so takes a launcher that can accelerate at least 50 tons to escape velocity in one shot. While one could express an architecture that could do it in more than one launch, simple statistics suggest that a segmented approach pushes mission risk unacceptably high. And simple economics suggests that the per mission costs consume more money that could be used in other ways, such as exploration systems at our destinations. Heavy lift in the class we are discussing is unique. No one else is building it. It is not something one can just go to industry and purchase. Our country built a heavy lift production and launch infrastructure, some of it here at the Kennedy Space Center, in Apollo, only to convert it to a low Earth orbit only capability in the space shuttle and discard the rest. The space shuttle is in fact a medium lift class system built on the remnants of a heavy lift infrastructure. Now we face a choice. Take this unique industrial capacity and either convert it or discard it. Either retool and rejuvenate our nation's heavy lift capacity or abandon it. These are not simple questions. There are benefits and costs associated with either path. Constellation, as it's defined today, is the manifestation of one of those paths. The path where heavy lift is the key to human exploration beyond Earth's influence. The path where the risk we take, be it technological risk or astronaut safety risk, should be on the frontier and not in the first 100 miles. We are executing this path today, and you've seen the evidence of it here these last 3 days. Our team has real hardware and test and fabrication, real designs we are maturing. And we are learning hard lessons every day as a team. We are indebted to our national leadership for the opportunity, once again, to dream and plan and build boldly as an agency and as a nation. It is at the heart, for me anyway, of what it is to be NASA. Teddy Roosevelt, in speaking of the American spirit, said it this way: "Thrice happy is the nation that has a glorious history. Far better it is to dare mighty things, to win glorious triumphs, even though checkered by failure, than to take rank with those poor spirits who neither enjoy much nor suffer much, because they live in the gray twilight that knows neither victory nor defeat." Daring mightily is what our father's generation did, at the expense of human life and national treasure, in order to blaze the trails necessary to even be here today, having this choice to make. They created the art of human spaceflight. Heavy lift, unprecedented crew safety for the first 100 miles. These are the choices that color our present plan, and we appreciate the burden that the committee sits with in weighing these options for our collective future. In these economic times, it is challenging to think of sizable financial investment to stimulate untold commerce. And we know you sit with our nation's constraints and challenges, an environment not unlike 40 years ago. We anxiously await your findings and decisions that rest in front of the nation, and we'll execute that plan, whatever shape it takes, to the best of our ability. Thank you for listening. We're happy to take questions.
Well, thank you very much. I suspect some of my colleagues do have questions. I've got a couple as always, but who would like to start out? Please, Bo.
Yeah. I have a question for Pepper, if I may. Do you know what is your cost to go in building Ares 1 unique infrastructure?
You mean how much do we have left?
Yes, how much you have to go? What will be expenditure to go to finish your unique Ares 1 infrastructure?
I'd have to get that number to you, Bo. I don't have that number off the top of my head.
If you can provide it to me, please.
Okay.
Thank you. And I have to Bob one question, Mike. Can I push my luck? Bob, you know, we in Huntsville, we heard about acoustics being one of the top risks on Ares 1. Are you guys going to get data in HiQ on Ares 1 that is meaningful enough to help those guys address HiQ acoustics? First of all, do you measure it? Are the Qs approximately equivalent?
Yes to all of those. We purposely put air acoustic high frequency instrumentation on our vehicle in locations requested by Ares and Orion to get the data they need specifically to address and get a better correlation for their models.
Okay, thank you.
Other questions? Chris?
Thank you. This is for Jeff. I just wanted to ask you if you could say a bit more, clarifying your remark. You said that one of the hard technical questions that remains is what does it mean to human rate a launch system? And you also said that the commercial sector will need to have these tough questions answered. I wasn't quite sure what you were trying to say there. Could you just expand on that a bit?
Sure. I think it centers around the issue of launch abort. Launch abort, I think, for our team has shown to be one of the toughest technical issues that we are wrestling with. Be able to abort throughout the trajectory, what we call no black zones. It's very, very tough to do. And then it also gets into the human rating requirements and how do we comply with them, okay? The first iteration of the human rating requirements from 3-4 years ago prescribed a peanut buttering of redundancy in systems, just too fault tolerant everywhere, and everything will be okay. And what we found out culturally, what that did was it caused designers to kind of disengage their brains a little bit. That particularly came to the fore not just for launch abort, but also in defining the Orion to be able to go to the moon and come back. Every ounce we take, since the Orion crew module particularly goes through the entire gear ratio all the way back to the Earth's surface, every ounce we put in the Orion is precious. It costs us from a performance perspective many, many times more than in other elements. So for every component we put in the Orion, we want to make sure that it is there for a reason, it's providing real value, it's mitigating real risk. And so this has tentacles into the topic Jeff brought up this morning on PRA. PRA is a tool, it's one piece of the data, but what we're really talking about is risk-based design, risk-based systems engineering. That is what we're really trying to foster around this notion of human rating. So the human rating requirements were recently, just in the last year or so, updated to prescribe only one fault tolerance and then demonstrate robustness in the design. And that can be done through either adding redundancy, just wrote out adding redundancy, or using a risk-based design approach to demonstrate why the robustness is sufficient with less than that. And that's kind of the approach. But that's the space we're living as we develop Orion and Ares 1. We're living the hard lessons of what does it mean to comply with these human rating requirements and feeding back those lessons to those that prescribe them to us. It should be pointed out the human rating requirements are not Constellation's requirements. They're the agency's requirements imposed on us, and we are doing our level best to comply with them. Just as any user that would want to be human rated would have to.
Norm, may I just follow up? I think you just described the difference between the 2A and the 2B versions of that document. Is that right?
Yes, that's correct.
In your view, is the 2B version sufficiently transparent for the commercial sector? Can they use that document and sort of tell transparently what they need to do to human rate a vehicle?
I believe that the B version of the document went a step in the right direction for helping anybody who wants to go about engineering a system to be human rated, to really give them some flexibility. Whereas wrote two fault tolerance everywhere, the prior prescription, as an example, was going to be problematic for a lot of folks. In a lot of cases, redundancy is not necessarily the right answer to manage risk.
Follow up.
Just a quick comment. I understand all you were just saying about the human rating standards and the lessons learned there, and there is valuable lessons learned there. I'm a little more vague on the lessons learned for the commercial vendors who may follow on the launch abort system, because I don't think anybody's designing a vehicle that has, a comparable set of environments that it would have to abort from to what the Ares 1 is going through. It's much more of a unique solution.
I think you're referring to the high Q environment that we fly.
Oh, the high Q, it's solid versus liquid. There's a whole host. I mean, it looks very different than the class of vehicles that would be following.
And I think what I'm referring to is sort of the methodology and thought process that would surround not the details of the physics of the design so much, but the thought process about how does one reason through and analyze and demonstrate then to the folks that they would have to be convinced that you've met 8705.2, the NASA standard for human rating. That methodology really is not written down anywhere. We're kind of going through it from our perspective. It is the first practical application of the standard and somebody trying to meet it. And so what the lessons learned that we will have would be really more along the methodology line that we'd be more than happy to share.
Anyone else?
May I have one more?
Yeah, sure.
Yeah, Pepper, in your briefing, you mentioned your MLP for Ares 1 is 50% complete, construction. And then you said that CDR is scheduled for June 2010. And my question is, it sounds to me like there is a little disconnect. Is the production too soon, or is it CDR too late?
No, it's not. It's what you see. 51% is the structure itself. There's a lot more to the mobile launcher than just the structure. What we've got to do is now outfit that structure. So all the ground systems, GSE that has to be built, has to be functionally tested out. All of that has to occur, and that's part of that overall life cycle for the mobile launcher itself.
So, but typically on any project that I've been involved with, you have a lot of changes between PDR and CDR. And you're halfway done manufacturing the thing that is at PDR level. And my question still appears to me that it's a high-risk approach. You're building things before you have, designed it, gone through CDR.
Well, I mean, obviously, I'd like to have all the vehicle requirements before I build the mobile launcher. Yeah, we're doing so at risk, but you have to execute the basic structure first, and then you have to follow with the interface requirements, which is really what we're going to build in the subsequent builds. So from a development standpoint, I think the risk is reasonable given that we don't have the opportunity to have all of the requirements on our plate when we're building the mobile launcher.
Okay, thank you.
Anyone else? My turn. I was pursuing, I think, the same line of thought that Bo was, and trying to understand the schedule chart here. VM2 in FY10, TBD, what is that date?
Okay, VM is a virtual mission. It is a process exercise to walk through the mission integration process.
Okay, that makes sense. Then the Orion, delete that. Ares 1Y is a launch in 14. Does that have an operational payload, or is it strictly a...
No, today it is defined as essentially not much more than a boilerplate Orion. It has been defined as a high-altitude abort test. The upper stage also has no engine, because the engine will not be ready by then.
How about the one that's just marked 1 about 6 months later?
Okay, Orion 1 is a full-up production stack of the entire Orion Ares 1
With an
system.
operational mission or a strictly test?
It'll be an orbital flight test, unmanned orbital flight test.
But not carrying any deliverable or anything?
No.
Let's see, then I wanted to ask, I'm trying to get a sense of what percent of the Orion 1 program is completed. And for example, if you could give us the latest data on the total dollars to complete, times 0 to total cost to complete, sure. And the total dollars expended or earned or whatever, earned value or whatever, both as a dollars and as a percent, and maybe the percent of drawings released on the whole program, not just the flight article, but the ground. Right. I'd like to get some sense of what the investment is as a fraction of where we have to go. Okay. And lastly, I don't recall seeing, and I may have missed it, but a cost per pound LEO plot for, I just said Orion, I meant the whole Constellation program, I'm sorry, yeah.
For phase 1, which is Orion, Ares 1, ground emission systems.
Exactly.
Okay.
Yeah, I'm sorry, I misspoke. I haven't seen a cost per pound to LEO for the Ares 1 compared with other interesting launch vehicles.
All right.
Yeah, I'm sure you've got that. If I could get a copy, Ed, you may have it, I don't know, but I haven't seen it.
Well, I was going to say, Norm, that we have in work with the program a fairly detailed budget analysis or cost profile analysis, so that before we task them to go off and do something else, which is probably a subset of that, we ought to coordinate. You may be looking for some additional information.
Yeah, I'd like to have apples and apples cost per pound versus alternative launch vehicles.
That's a different request, but in terms of
The percent complete
and cost to go and so forth, we got that in the works.
Okay, why don't you hold on the first one, and Ed, if you don't come up with it, if you would alert the folks, and otherwise I'll assume that we'll get it.
Okay, at a high level, and I think Steve Cook described this yesterday, we're roughly in the 30% complete range,
Okay.
where you'd kind of expect to be at PDR.
Yeah, that's helpful to.
Okay.
I think that was all I had. Yeah, I think that takes care of it. Oh, I know what it was. I did want to ask, to what extent is this schedule defined by the amount of funds that are available? And if you were to have an optimum schedule from an engineering standpoint, what would it do to the IOC?
Well, it's definitely not optimal from an engineering standpoint today because of the shape of our funding curve, as we've discussed, and I think Aerospace touched on yesterday.
But if you were to do an optimum?
If it do optimally, the confidence in achieving the March of 2015 date would obviously increase. Would we be able to accelerate earlier than March of 2015? That's problematic at this point. There's so much water under the bridge at this point. We're so far down the road in terms of getting long lead items and engineering development units procured. More money in FY10 would improve our situation, but it's probably just going to increase our confidence that we'll achieve March of 2015 and not really accelerate anything.
But really, I had more of an academic question in mind. That was the penalty we paid by not laying out an optimal engineering program in terms of schedule for a given confidence level.
Correct. The confidence level planning, I hope I'm answering your question. Confidence level planning that we had done really is where the March of 2015 date came from. Today, the program sits at 67% confidence on cost. I wish I could say that on schedule, but that's not true. Today, we have a suite of schedule confidence assessments, 6 or 8 different models and ways of looking at the schedule confidence that range anywhere from just a few months late on the March of 2015 date to up to 2 years late. And that's, again, as I touched on the other day, it's a little bit like hurricane forecasting and where you're going to make landfall. Has more meaning here, I think, today than it did in Huntsville, but.
Okay, I guess I was just going to make an observation too. I was struck by the earlier discussion on reliability that with the expendables, where we put large, expensive military payloads on them, and the point that we do go to a lot of effort to be sure they're reliable just because of the dollar investment and the operational implications. And then I think back again to when we man-rated Atlas and Titans early on, and those vehicles were designed as ICBMs, which I don't remember the design criteria, but I remember some of what we used operationally in figuring targeting, and it was not a very reliable vehicle, and yet we got those man-rated.
Well, and I would say that the human rating requirements as they exist, there are provisions for tailoring, given for the specific situation. So someone, an Atlas or a Delta or a SpaceX could come in and work with NASA to tailor a human rating plan that NASA would then review and either accept or not, and then go forward, and then that entity just meets their plan.
I think that's an important point to be made, and I guess I might, does anyone else have anything you want to say at this part of the discussion? Okay, Wanda, then Bo. Let me get Wanda first. I saw her first.
I would just offer, and we touched on it in the evaluation process, that it is striking the balance between, the mission capability and, how safe do we need to be. You mentioned the early days human rating on the Atlas and the Titan, and I don't know that anybody's gone back and looked at the difference between what we considered human rating then versus what we're aiming for now, but I suspect that, we would find a big difference.
Yeah, I do too.
I think the opportunity is to make sure that we provide or enable the commercial folks to come in and understand what we mean by human rating, and as Jeff just described it, that you need to demonstrate the robustness, and if we have a standard that applies across the board, that everybody understands that we have an opportunity to have new entrants.
Standard's definitely the beginning of the conversation, not the end.
Yeah, exactly. Bo?
Norm, I just want to make sure that we understand what Jeff said, and see if you agree with what I'm going to say. You say you have a 67% schedule confidence, cost confidence level. You have low, you didn't say it, but I heard you say it previously, you have a low schedule confidence.
Today.
Which
let
me read this the way I heard it and see if you agree. That means that if you blow schedule, you will spend additional money, and your cost confidence really isn't all that meaningful.
Well, that you have to combine that with the reserves that we have protected. We have a 1 year slip of reserves in our budget already set aside, in addition to the run-out cost that coincides with the 67% cost confidence number. Now, I should point out that the program is still in the formulation phase. We will not be complete with formulation until next year. We are taking significant remedial action on our schedules to increase the schedule confidence, so that when we petition to the agency to be an approved program next year, we can close our business case, because business case on cost, on schedule, and on technical performance.
But your high confidence in cost does not reflect the fact that if you blow schedule, your cost was going to be higher. Doesn't reflect that coupling, which I think was the source of some of the differences we saw in aerospace numbers and your team. Yeah. I just want to make sure we understand that.
Yes, and those are some of the details and assessments that we will share when we meet with aerospace next week, as at the request of the panel. We'll share with them all the assessments we've done on both cost confidence, schedule confidence, and joint cost and schedule confidence level.
They'll also share with your team how they show this coupling between cost and schedule confidence.
And as discussed yesterday, we may agree to disagree, or we may be able to close some gaps.
Jeff, I used to live in a country where everyone agreed. It was under communism. Thanks to God we live in America. We can't disagree, as long as we understand each other.
Yes.
Well, thank you very much did you want to say something, Ed?
Yeah, Jeff, could you just give us a few words on what is the critical path through to the first Ares Orion flight? Sure. Because we've heard from various people that we might be able to accelerate this, we might be able to accelerate that, and I understand that there's a lot of fuzz on it, but are the booster and the capsule basically both on the critical path at this point?
They're very close. The pacing item on the booster is the upper stage engine, the J2X. We've moved forward as rapidly as we could. A rocket engine development historically takes on the order of 7 years. We're going to have an engine to test in about 40 months, which is historically very good for a rocket engine development. We'll get it into test at the end of next year. Getting enough runtime on that engine to certify it is the pacing item essentially on the rocket side. The spacecraft is really been affected greatly by the budget, the shape of the budget. The ability to buy long lead parts and engineering development risk reduction hardware has been limited. We've prioritized our work. We've spent our money on the most critical things. But because not everything has been able to be purchased and get in the pipeline, there's going to be, that's essentially the critical path for Orion runs right through the supply chain at this point. So that's what we're scrubbing on right now, and we're working very closely with Lockheed Martin, with their suppliers, to see if we can improve that. And I will say we've already improved it by the budget that I provided to the project in the most recent budget exercise. I was able to plus them up in 9 and 10 by several $100 million, and that is going to help greatly with improving Orion's schedule.
Well, thank you so much. You've taken a great deal of your time to keep us up to speed here during this, 60 days or something we've been working, particularly this week. We appreciate it a lot. We'll probably be back with more questions the next week or so, but we'll give you a break here for now. Thank you.
Thank you very much.
Indeed. And since that completes the technical discussion for the day, I might just, since we were talking about the reliability of expendable launch vehicles, I might just take a moment to share a story that seems apropos. That the company I used to serve was preparing to launch an expendable launch vehicle, a very valuable one from a cost standpoint, and on top of it that we had built, and on top of it was a spacecraft we had built that was extremely valuable from a cost standpoint. We had one of our members of our board of directors was the CEO of a very large insurance company in this country, and he came to me and said he was not a technical guy at all. He came and said that he'd like to go watch that launch. And I said, well, sure, we'll arrange that, but why your particular interest in this launch? Because he'd never expressed any interest. And he looked at me and he said, because I've never seen a corporation's entire equity rise off of a launch pad before. I think that's a little bit the challenge that we're looking at here.